So for discrete global symmetries, there's no conserved current, okay? But we do have a topological operator. But there do exist topological operators U sub G. All right? So let me just give you an example. I think the simplest discrete symmetry is imagine a real scalar field phi of x with a Z2 symmetry. Phi goes to minus phi. Okay? So, you can take whatever action you like. Delta phi squared plus some arbitrary potential of phi squared. Then there exists a topological defect which I'm just going to call U sub Z2, okay? Which again, you can define on any codimension 1 manifold. I'm calling it U sub Z2 because really the thing labeling it should be an element of the symmetry group, but Z2 has only one non-trivial element, so I can just call it U sub Z2. And the role of U sub Z2 is to generate the action of the symmetry. So, for example, if I act, if I act with U sub Z2, I keep writing S2, D minus 1, on my local field phi. So again, if I collapse it onto the local field, it does the action of the symmetry, which just gives you minus the local field. Okay? Furthermore, if you fuse two of these guys together, so if I take U sub Z2 on some thing, and again, another one on a neighboring thing, like in that picture, then the fusion of these two things together works with group composition. But of course, if you take an element of Z2 squared, you just get 1, the identity. And therefore, this thing is its own inverse. Right? So if I take the Z2 topological defect, take another one, and fuse them together, you just get nothing. Yeah?
So you said you're thinking about Euclidean space mainly.
Yeah.
In the end, you probably also want to have a real space picture.
Yeah, it's good to have one, yes.
So these spheres that you are drawing, should one think about them as spheres in some kind of Minkowski?
So in Minkowski, I think I'm uncomfortable with the idea of having a sphere in Minkowski. That feels wrong. I think the way to think about it in Minkowski is really to go to a Hamiltonian picture. Then you can take this sphere and kind of deform it into like two sheets of charge. Like take the sphere, blob it out into something like this and something like this with time going like that. And then in a Hilbert space picture, that becomes a commutator. And that's, I think, the best way to think about it in Minkowski. I don't like the idea of having time and drawing a sphere in Minkowski. That's not good. Yeah. They don't wrap anything. Yeah, so that's also not correct. So I think the way to do this, there's a way always to translate these things into the language of commutators. And I think that's what you should do if you're doing it in Minkowski. Yeah, absolutely. So this is just a rephrasing of that. There's nothing fancy, but the geometry is nice. Yeah. Good. Excellent question. Any other questions? Okay. So yeah. So again, the takeaway point here is for discrete symmetries, you also have these topological operators. All right. Okay. And one more point is, again, these topological operators are also called, as I mentioned last time, I'm just saying this again, they're called charge defects in the literature, and I will use this language as well. Okay. Good. Now we are ready to move on to higher form symmetries. Okay. So this is chapter 2. Okay. So the basic idea is once we realize that global symmetries are associated with topological objects in a theory, we can generalize this in many different ways. Okay? The first one we're going to do is generalizing it so that the dimensionality of this is different and no longer codimension 1, and we'll see what that means. The second thing we're going to do is generalize it so that the composition law that we have will change and no longer be a simple group composition law like that one. Okay, these are the two directions we're going to take in these lectures. And we'll see that this generalization, you can motivate it from a sort of mathematical point of view, but they exist in many normal field theories. Okay, they have these symmetries. So it's really a very productive thing to do, even if you're trying to do very applied things. I got into this field because I was trying to develop a theory for magnetohydrodynamics, and that is how I entered into this thing. So it's a very useful thing no matter how applied you are. So higher form symmetries, they basically answer the following question. So normal symmetries are associated with a conservation of particle number. Right? We saw that yesterday. Normal symmetries count particles. But in life, sometimes you have things that you have more things than particles. You might have extended objects like strings or branes or things like that. Okay? It's not just in string theory that you have things like that. They really exist in real life as well. You see, magnetic field lines, for example, exist in real life. Magnetic field lines are extended objects. They're strings. Okay? And they're conserved. So you should ask, what is the symmetry principle that does the same thing for strings, branes, other large things that normal symmetries do for particles? And the answer to that question is, the symmetry principle is what's called higher form symmetries. Okay? So let's first develop the theory, and then we will look at some examples. A lot of examples, actually. Okay? So first, we're going to do this in the continuous case. So in the continuous case, if you have a continuous higher form symmetry, what that means is there exists an antisymmetric two-form current. Okay? So here, J mu nu is an antisymmetric two-index object. Okay? This means antisymmetrized, these brackets. Okay? So J mu nu is a two-index conserved current. So because it's conserved, that means that we have partial mu, J mu nu equals to 0. Or in form language, d star j equals to 0. Okay, so basically I have added one extra index to the story I told you yesterday. All right. So just as ordinary global symmetries count particles, this current counts strings. Okay. We say that this is the current for what's called a one-form global symmetry. Okay? The 1 is because that thing has 2 indices, and 1 is 1 less than 2. We're stuck with this notation. It makes sense a little bit later. But the number of indices of the current is 1 more than the forminess of the symmetry. Okay? So in that language, the normal one that we know and love is nowadays called a zero-form global symmetry. Okay? So the symmetries I discussed yesterday were all zero-form. This is a one-form global symmetry. Okay. Now, I claim this counts strings. Okay? Just like a normal symmetry counts particles. Let's understand how this is. At some basic level, you see that extra index, the new index that I have there, that index sort of tells you which way the string points. Okay, that's basically what it's doing. All right? That should seem plausible. So let's dig into this a little bit. Basically, what we want to do is we want to construct a conserved string number, a charge, okay? So how do we do that? We do that by integrating that object, right? That's what we did in the normal zero form case. We integrated j, and we got some conserved number. So let's do the same thing. We can now form the following object. We can form Q, which is now defined on a codimension 2 manifold, not a codimension 1 manifold, okay? And in indices, this thing looks like this. You integrate, oops, I left out a d to the d minus 2x root h n mu nu j mu nu. And in forms, this looks like this, star j. Okay, so what's happening here? Here I'm just writing this out in normal index notation. Okay, so this n mu nu is because if I have a codimension 2 object, it has not one normal vector, but 2 normal vectors. All right, n mu nu is the outer product of those 2 normal vectors. This is the sort of nice geometric measure you can form on this. But really, this is just integral star j. Okay, so if you use differential forms, j is a 2 form, star j is a d minus 2 form, so it is naturally integrated over a d minus 2 manifold. Okay, okay. But what does this mean physically? Let's think about this. So let us imagine that I have a bunch of strings that are poking through this blackboard, okay, towards you. And the strings have no end. They can't end, all right? And you want to count the strings. How do you do it? Well, you see, if you were counting particles, you'd have to integrate over the full volume of the room to get every particle, right? But because you have strings, you no longer need to count the full volume because every string will poke through the blackboard. So you just need to integrate over the blackboard, which is a codimension 2 manifold, and then you can move that up in time and get the same answer, or you can move it forward in space and get the same answer, okay? So because strings have one extra dimension, counting them involves doing an integral of one lower dimension. Does that make sense to everybody? Okay, good. I just want to draw a quick little picture of what I just said. This picture is a little bit less obvious than the picture that I drew for particles, but I think it is helpful. So let's imagine here are some string world sheets, okay? So string world sheets are 2-dimensional objects, all right? So there's some string world sheets. They live for all time, and they extend in one spatial direction. And now, this is a 3-dimensional world, of course. This picture here is some 3-dimensional world. So a codimension 2 manifold is a line in this 3-dimensional world. Okay? So here is my Q of md minus 2. And so notice that I can drag this guy in space or in time, and I always get the same answer, provided all these string world sheets have no end. Okay? This is just a picture of what I just told you in words. All right? And it's the same picture that's appearing here. Right? So to be clear, because d star j equals to 0, that implies that Q of md minus 2 is a topological defect. Okay? You can move it in space, you can move it in time, and you can wiggle it however you like, and you will still get the same answer. Okay, good. So now the reason why we spent a whole lecture formulating normal symmetries in this fancy way last time was because now we can basically take all of the machinery that we had last time and pretty much just apply it, just be drawing slightly different pictures. Okay? So we should repeat everything that we do for normal symmetries now in this higher form framework. So the first question is, what is the charged object? Okay. So for a normal symmetry, the charged object was a local operator because a local operator made the thing that you count, which was a particle. What is the object that makes the thing that you count here? Well, if you want to make a string, what you have to do is you act in your theory with a line operator, right? You act with a line operator which says, I am creating a string along this line. And you let it go, and the string does its thing in time and does whatever it wants. In other words, the thing that creates a string is a line operator. You can imagine it as the boundary of one of these two-dimensional string worldsheets. So the charged object is a line operator defined on a one-dimensional curve. Okay. So I will use the notation W of C to refer to most line operators. This is, of course, inspired by Wilson lines, and we'll see soon that Wilson lines are an example of this sort of line operator, though not in every theory, only in some theories. Okay? Okay. So given that we have this, that a line operator is charged, we should, yeah?
I mean, this only holds if the lines are not closed, right?
They should actually be closed, sorry. They should be closed curves. It only holds if the operators have no endpoints. That's when it holds. Is that what you meant by closed, or?
But you say that these are then infinitely extended in time.
Yeah, they create a string, and that string worldsheet lives for all time. Yeah. Does that make sense? Yeah, okay. So strictly speaking, this holds when they have no endpoints. That's really important. The interpretation is actually somewhat different if they wrap a non-trivial cycle, or if they go off to infinity, or if they're contractible. It's all a little bit different, but we're going to explore all of that. And there's information in each of those cases. Yeah, question? No.
I think it was basically the same. I was asking whether you have a closed string.
Yeah, closed. So you're saying if you have a closed string, so what you're imagining is there's a closed two-dimensional worldsheet of some. Is that what you mean, or by closed do you mean that the two-dimensional worldsheet has no endpoint? Like is the two-dimensional string worldsheet like this, or it wraps a cylinder? You're saying something like that. Yep. So then you can imagine that in the distant past you acted with one of these guys to make the string. So this has a boundary at some point, and you acted with this in the distant past to make the string. That's something that you might imagine.
Can I find all this in somehow really line that definitely will cut through the cylinder so we count it?
I see what you mean. Let me think about this carefully. So in the case of the cylinder, so it's sort of this depends a little bit on details. Are you imagining a cylinder in a two-dimensional world or a three-dimensional world, or in this picture? So in this picture, so this is a three-dimensional world. Then the truth is, this actually doesn't obviously carry string charge, because most of the time, if you hit it with something like this, then you're going to get a +1 and a -1. So you're saying, what you're really saying is, you have a closed string sitting in the two-dimensional world. Does this carry a net charge? And it does not, because it can be shrunk to 0 and collapsed. Okay. Having said that, there is still information present, even though it doesn't carry net charge, because there's a local string density which is non-zero, which is still a very useful thing to think about. This is different, on the other hand, if you imagine that the cycle that the string wraps is non-contractible, then it does carry a net charge, because then I can't draw this picture in this way. So each of these cases is something one should study on a case-by-case basis, but I claim that in all of those cases, you can extract some useful information from it. Okay. But exactly what we're going to talk about. All these details we're going to discuss. Yeah? Sorry, coming in the side, going out the bottom like this, or yeah. Is the line operator, or what is the line? We have to now. This is the sort of fun of the game. You have to distinguish: is this the line that creates the string, or the thing that measures the charge? Topological defect that measures this. Yeah. So if you imagine doing something like that, then really you have to really explain what you mean by go out the bottom. Okay? Because the string has no end, right? So because of that, there's no bottom unless you go all the way to the point where this was created by the line operator, right? In that case, you're basically linking that thing, and we're going to talk about that in a second. Yeah, good. Yeah, but indeed. So one has to be very careful about exactly what you mean, but you can always figure it out by the rules I'm going to tell you, and yeah, it's a fun game to do. Okay, so I've not told you the rules yet, but let's now figure out what the rules are for all these things. So I claim that the line operator is what is charged under the symmetry. So the first thing I should do is write down the Ward identity for this conserved current in the presence of the symmetry. Okay, so let's do that. It will not fit here, so I'm already moving here. Okay, so what is the Ward identity? for the one-form symmetry. So what I want to do is write down a formula that tells me that the current is not quite conserved in the presence of the charged object. So let's do that. What we have is d mu j mu nu at some point x. And then I have my line operator defined on some curve, some one-dimensional curve C. Okay. Here is my C. And so from this point on, I am going to introduce a charge. So this is charge that has charge Q. Okay? And the Ward identity looks like this. This looks a little bit complicated. Let me just break this down for you. So I have my curve C, okay? So I'm calling x sub c of s is the coordinates of the curve C as I move, okay? So here s is a parameter along the curve, all right? So x mu c of s is the actual physical coordinates of that curve. And so what this is really saying is that the current is not conserved if my point x, where I'm evaluating the current, hits the curve C. That's what this means, okay? It's integrating along the curve, and it's a delta function so that whenever x hits this curve, it's not conserved, all right? So notice that this index here, in other words, the direction that the curve points, is what provides the extra index that we need on the left-hand side, okay? That should make sense. It should also make sense why it had to be a line operator. We have exactly one index to deal with in this. Okay, that makes sense to everybody? This is an annoying expression. This is actually a very annoying expression. Okay, so I want to write this in a more elegant way using differential forms. So this is just clunky, but it says not conserved if x is on the curve C. That's all that this means. Okay, so now I'm going to introduce a more elegant notation for this same thing. All right. So I'm going to define, so to make this notation better, this is, I stress, really just notation, but I'm going to define, let me get these numbers right, a d minus p form delta function. Form valued delta function. Which is going to be called delta sub c sub p of x. Okay? So delta sub c sub p of x depends on a p-dimensional submanifold. C sub p, which is some subset of Rd. Okay? So it takes as input a p manifold, C sub p. It depends on x, which is in Rd. Okay? And basically, this thing is a delta function where x has support if x is on Cp. That's it. Okay, that's what this means. All right? But let me just write down the formulas that satisfies. Okay? So in particular, this is 0. Let's see. Delta sub c sub p of x equals to 0 if x is not on Cp. Okay? So here's my Cp. If x is not on Cp, it's equal to 0. Okay? And it also integrates to 1 you should think, what does integrates to 1 actually mean in this case? What it means is, for all test forms, So for all differential forms, B sub p, it is a fact that if you integrate R over RD, B sub p wedge delta C sub p of x, that is equal to the integral on C sub p of the form BP. Okay. So this is just notation, but let me just again emphasize what this means. What this side is saying is you're integrating some form over all of space multiplied by this delta function, okay? And the final answer has only the integral along this CP, okay? So the parts that weren't on CP are 0 and don't contribute. The parts that are on CP contribute in the obvious way, okay? So this makes sense to everyone? It's just notation, all right? And it is a surprising, it's fun to actually, if you've not seen this before, which I confess I hadn't until I started working in this, it's fun to actually write this out in local coordinates. It makes sense and everything. It's a nice object. But in particular, that case is for p equals to 1. And I can now write down this conservation law in a nice way. D star j in the presence of WC, so this is D star j at the point x, is equal to I times q times delta c of x times W of c. Okay? So this is the Ward identity for, sorry, I'm a little bit unhappy with the way I wrote this. Let me just fix this. D star j of x. So d star j of x in the presence of WC is equal to this delta function on the curve WC. Okay? All right. So this is exactly equivalent to that thing with the integral. Good. So I'm amazingly already out of board space, so now I will begin the process of erasing them. But are there any questions before we get into that? Okay. All right. While I erase the boards, everyone should compute that form value delta function for, I don't know, a great circle in R3, say. Good exercise. Good exercise in polar coordinates. Right. Any questions while we wait for the 1 second to this to dry? Nope. Okay, we'll just wait. So the next thing that we're going to do is generate the topological object that creates the finite rotations. Okay. So in particular, this one is just as wet. Yeah. Okay. So so what we're going to do is construct the object that generates the finite rotations. So I have already constructed the charge. I've erased it. Sorry, but we can construct the object who generates the finite rotation. So now that we have q of m, d minus 2, this creates an infinitesimal rotation. We can now create the object that generates the finite rotation. And that's generated by something which I'm going to call u sub alpha md minus 2. And just as in the 0 form case, this is e to the I alpha q as a function of m d minus 2. And what you should now ask is, what happens if you take this guy and drag it through a line operator? Okay? And just like in the 0 form case, this thing is not topological if you drag it through a line operator. And again, the simplest way to think about this is to imagine taking your line operator, W of C, and now wrapping it with some u alpha, which is defined on some SD minus 2. Okay? If you take this u alpha SD minus 2 and collapse it, then it will act on the line operator by a phase, which in this case is e to the I alpha q times the line operator. Okay? So, and again, just a formula without the picture. U alpha SD minus 2 on W of C equals to e to the I alpha q on W of C. Okay. So this follows from that formula there. Okay, you can prove it from that. Again, this picture makes sense because a D minus 2 thing links a one manifold. All right. In particular, this picture is actually for the case D equals to 3. In this case, these are both one-dimensional lines. And as we know from shoelaces, one-dimensional lines link in 3 dimensions. Okay? Okay. So this is the idea. This, everything I just told you, is for a one-form symmetry. It's just this. And it should be pretty obvious how to take the idea of a one-form symmetry and generalize it to a p-form symmetry. Okay? This is left as an exercise, but it should now be pretty clear to you how to do this for all p. Right? The dimensionalities of these objects differ, but the key point is that you always want the thing that is charged to link with the thing that measures the charge. Okay? And it should also be clear that all of our lives, what we've been doing, is really a very special case where the charged object is just a point. All right? Okay. Any questions about this before we keep going? No. Yeah.
So if I would look at the zero form, so just functions,
Yeah.
I would have difficulties to imagine like the SD sphere in RD.
You know, imagining is a luxury. You know, I also cannot imagine any sphere with dimension higher than 3. But the formalism works fine, right? That's the case that we discussed all this time. If you have the zero form was the case of last time. So then the operator is a point, right? The charged operator is a point, and you have a D minus 1 sphere that wraps it. And so I agree it's hard to imagine for D greater than 3, but the formalism works, basically. Yeah. Yeah. Does that answer the question? Or yeah.
So what would be the charged operators then?
So this is the case of yesterday. The charged operators are local operators, okay? And the charge, the thing that measures the charge, is a normal charge from normal physics, where you integrate sort of over a codimension 1 manifold, like a time slice.
But this is the case for the normal symmetries, right?
Yeah, that's right. Yeah.
So this is where I start with the 1 form?
Yeah.
So what's happening if I start with the 0 form?
So 0 form is normal symmetries. 0 form is just another name for normal symmetries. So the symmetries you've studied all of your life are 0 form symmetries. Okay, does that make sense?
I think I said it in a bad way. What I meant is like if I start where my gauge field is a 0 form.
Oh, I see. If your gauge field is a 0 form, I think that's really just a fancy way to talk about. So the truth is, this doesn't really need a gauge field, right? I've not discussed any fields or anything yet. So the case where a gauge field is a 0 form is really just basically a scalar, right? Your gauge field is at a scalar. And then you can apply all of this machinery in this case in a certain way. But the truth is, even that case where you have a 0 form gauge field or scalar actually has some higher form symmetries present in it. So you can apply lots of this machinery to that case. Yeah. Does that answer the question? Yeah. Okay, good. Good. I should stress, by the way, so far there are no gauge fields, right? This is just stuff. I have line objects, I braid them, they have linking, you know, okay? So this is a description, independent statement, everything I've said, all right? And so the point is that whenever you have 2 objects that have a non-trivial linking, then you can call that a symmetry. It's useful to think of it as a symmetry, okay? All right. What else did I want to say here? And so you can generalize this to P form. And then for any P, you're just counting higher and higher dimensional objects, right? 0 form means that you count particles. 1 form means that you count strings. 2 form means that you count like sort of a bedsheet type objects. For any higher dimension, there's no words for it, but you get the idea. Okay. Now, so you can generalize from 1 form to P form with no problem, all right? However, there's something you cannot do. You cannot generalize this to a non-Abelian symmetry. Okay, let's understand why that is. So there are no non-abelian p-form symmetries for p greater than 0. Okay. Let's understand why that is. Okay. So in particular, let's try to imagine the group composition law. So imagine that I have a p-form symmetry, which means that I have some sort of a charge generator on a d minus p minus 1 manifold. Okay, did I do that right? Yeah, okay. So if I have a p-form symmetry, I have some charge generator u sub g on a codimension p plus 1 dimensional manifold. So now imagine taking two of these, they're topological, and fusing them, okay? So I have g, u sub g, and u sub g prime, and now I fuse them, and I get u sub g, g prime of m d minus p minus 1. Okay. So this is the sort of natural fusion law that I have to have when I compose two of these things, right? But now notice that there's something different now in the p-form case. Because you see, there is no ordering of u sub g and u sub g prime, all right? In the codimension 1 case, I could really say one of them is in front of the other, and that makes sense. But in the higher codimension case, there is no way to say that one is in front of the other. I can always rotate these two things around each other and put them in any ordering that I like, okay? So there is no notion where g is in front of g prime, which means that there cannot be an ordering on this side as well, which means that this must be equal to this, okay? Which means that the group from which I draw these things, the group of g's, is necessarily abelian. Okay. So that's sort of interesting and in a sense kind of disappointing, right? You sort of, I'm going to use a non-abelian gauge theory, but it's clear immediately I'm not going to have a non-abelian higher form symmetry. All right? Okay, but that is life. So you cannot have non-abelian symmetries. However, you can easily have discrete ones. Okay. Because these discrete symmetries are necessarily abelian, they're basically all just z sub n. I mean, okay, you can take like products of them and so on, but they're more or less just all z sub n and various ways to combine z sub n's into each other. So in particular, z sub n is going to play an important role in what's going to happen. Okay. So just to be clear, that's going to mean something like u sub g, where g is an element of Zn. Okay. All right. So that's the formalism. How are we doing? So I think it might make sense, actually. I think what we're going to do now is, this is actually an actual time to take a break. So let's take a break now and come back at 10:30 in 10 minutes. Okay? Yeah. Okay, cool. And I'll go straight for the last hour. Okay, and I'll be around if anyone has questions. Yeah. Oh, that's yeah. Yeah. Exactly. Yeah. So sadly, because they have to be abelian, I can't. There will never be one with a non-abelian discrete group, which means that I'm now interested only in abelian discrete groups. And I don't know. It's kind of basically Zn, right? I think. And
yeah.
I guess there's semi-direct products and stuff, but it's more or less just Zn. Yeah.
Okay, but I guess it's more interesting than the abelian Lie groups, right? Because abelian Lie groups are just products of UNs, but at least you can have like Z mods.
Yeah, I guess. Yeah, interesting is always a bit subjective, but there's rich physics that comes from that case. Yeah, exactly. Yeah.
Sorry.
Yeah.
I couldn't understand why this has to be abelian, because if I make the same case for zero form symmetries, we can rotate again. That's what I'm thinking, because you said like we can rotate in this case, and it'll be still be abelian.
Yeah. So good. So let's think about the case in 3D. Okay. So in 3D, in the zero form case, we have two-dimensional charge defects, right? Okay. So if I have two-dimensional things, so really the full information is really here in the hands. So in 3D, if you have zero form, then there's a sense where this guy is in front. If I have an infinite sheet and an infinite sheet, this one is in front of this one. That's a fact. I can never deform them so that this one will be on the other side, right? So there's a natural ordering of these two-dimensional objects, right? Okay. Even though they're topological. Okay, now let's go up one forminess. So now I'm doing one-form symmetries, okay? So now they're one-dimensional objects in 3D, okay? So notice that there's no way anymore for me to say this is in front of this, because I can continuously deform them until this is in front of that, okay? So there is just no ordering anymore, and there's no way to get anything non-abelian. Yeah. This picture is really what's happening. You know, that's really it. Okay. Make sense? Yeah, good. Okay. Yeah.
Regarding to this one, so
yeah.
right now those U's with the same codimension manifold, right? Or the same submanifold. So I'm actually looking at the same sheets, don't I? So if I look at the same sheets, I don't really see which one is first because they are actually the same.
Yeah, so I think the right way to say this is if you take two of them on different sheets, then you can fuse them into something on one sheet. But the one that you get, like which guy you get on the same sheet, depends on whether you fuse this one from the left or fuse it from the right. You get a different object on the single sheet. Does that make sense? I should write a formula for that. That was a bit, you know. So imagine that I take this guy and this guy, okay? So I have U sub g and U sub g prime, and I fuse them, then I will get something which is on just one sheet, which is U of gg prime, okay? On the other hand, if I do it the other way, U g prime, U g, then I will get something which is a different element, which is U g prime, U g, okay? These are just different things, okay? But if they're ever not the same, then, you know, now does that answer the question? Yeah, good question. Yeah. Okay, welcome back, everyone. I received a few questions about sort of what do I mean when I say something holds in the path integral. What I really mean is, sorry, this is not very well written. What I really mean when I say something holds in the path integral is that I really mean something like this, okay? You have some theory, you do some path integral, you think about two different things, you know, O of x, O of y, where O is like phi squared or phi cubed or whatever. And then that's equal to something different, you know. So this is some other thing, okay? When I say something holds in the path integral, I mean doing a path integral with that stuff is equal to doing the path integral with the other stuff in front of this action, okay? This is what we normally mean when we say something holds as an equation of motion in quantum field theory. We typically mean this, okay? Like if you take your quantum field theory, you look at your classical equation of motion, then it more or less holds in the quantum theory. We say something like it holds in the path integral. It means this, okay? Does that make sense to everyone? Okay. So, yeah. Yeah.
Holds in the path integral.
Yeah.
Everything commutes, right?
Yeah, exactly. Exactly. So that's an important point. Let me stress that here I'm doing a path integral. So let me just make this phi, okay? This phi and this guy phi squared, say, just so that they're different. This is a stupid thing to calculate, but you get the idea. You see, these are just numbers, right, that I'm integrating over in the path integral. So these things commute. But of course, this is related to something in the Hilbert space picture. The ordering of these things in the Hilbert space picture comes from the time ordering in the path integral. This is just basic path integralology, but it's good to be reminded of it. Okay? Okay. Yeah, yes?
So when you write it like this,
yeah.
that needs to be the function of x and y.
Yeah, this is not good. Yeah, yeah, that's right. This is, sorry, I cannot imagine when this would happen. Yeah, but this is just a notational example. I regret using this notation now. Yeah, indeed. Thank you. Yes. Okay. Good. Okay. Yeah. Okay. So, all right, now let's get back to the main thrust of this. So we have understood that there are one-form symmetries. And now what we now need to do is we have to do everything that we did for normal symmetries, which really takes a long time. It's like most of quantum field theory, and do it again for higher form symmetries. And that's what we're going to do for the next few lectures, okay? So the way I'm going to do this is I'm going to first describe different phases of higher form symmetries or of one form symmetry, and then I'm going to do a series of examples, okay? Yeah.
Could you give one example of maybe like
Yeah, good. Let me give you one example first. Yeah. So electromagnetism has extended objects in it. by which I mean there are magnetic field lines and there are electric field lines. Okay? Those are strings. They have conserved fluxes associated with them. Electric flux is conserved. I mean free electromagnetism, F square. Action is F square. Okay? Electric field lines don't end. Magnetic field lines don't end. That means that there are two one-form symmetries present in electromagnetism. Okay? Okay. So I'll do this in great detail in the rest of it, but that's an example you can keep in mind when I now discuss the phases. Does that answer? This is, I think, the simplest example. Yeah. Okay. Good. Okay. So now, with everyone in the back of their mind, let's now discuss phases of one-form symmetry. Yeah, oh good, thank you. Phases of one-form symmetry. Okay. So if you recall, when I talked about phases of symmetry yesterday, feels like a long time ago now, but it was just yesterday. What I did was I started by diagnosing different phases by looking at the behavior of the charged operator, right? I had my local operator O who was charged, and I looked at how its two-point function behaved, and that was very different in two different phases, and that's how we identified the different phases. I now want to do the same for one-form symmetry. So what I should do is I should look at the long-distance behavior of the charged operator who is W of C. Okay? So everything I'm going to do now is going to parallel the zero-form case. The first phase you can have is when the symmetry is unbroken. Okay? In the unbroken phase, so here, let me call this the unbroken phase, then for large C, what we have is W of C, as C becomes large, this thing is a function null of the curve C, and the precise functional that one gets is that this goes like the exponential of minus the area enclosed by the curve C. Okay? This is what we have when the symmetry is unbroken. So this area of C, to be more clear, this is the area of the minimal surface S such that the boundary of S is C. Okay? So in other words, what we're looking at, let me make this approximate equal sign. What we're looking at is you have some sort of curve C, okay? So you're evaluating the expectation, sorry, I should have said that. This is the expectation value of the Wilson line. Of the line operator. It's not, you don't know what Wilson line's yet. Of the line operator. Okay, the expectation value of the line operator goes like the exponential minus some number times the area of the curve C. So you take your curve C, which is some closed loop. You look at the minimal surface that fills this in. This minimal surface has an area. This expectation value goes like the area. Okay? Now, there are a few things that I want to say about this. First of all, this is the higher form analog of the exponential decay of correlation functions that we saw previously, right? Let me just remind you why that is. So this is the higher form analog of when we had O dagger X, O Y goes like the exponential of M, X minus Y. In this case, I had 2 points. I connected the 2 points by a line. The length of that line determined the correlation function. Here, I have some curve. I fill in the curve with a surface. The area of that surface, it's like the length of the line, determines the expectation value. Okay? In this case, this happened because the particles were very massive, and that's what created this sort of action weight in this path integral. Over here, this is happening because, so that closes this. So why does this happen? The unbroken phase means the things that I count, the strings, are very heavy. okay? Which means that they have a finite tension. T. That T is the number that appears here, okay? So what's happening is when I insert this line operator creates a string worldsheet. That string worldsheet tries to minimize its action and sort of fills this thing in the minimal possible way, and that's what results in this area law, okay? It's really a direct analog of what's happening here, just for strings instead. Okay. Does that make sense to everybody? Yeah. Good. You can never have one that's open, but you could, for example, imagine wrapping some sort of non-trivial cycle, right? That's what you're imagining, I think. So this is a good point. If we have W of C in the unbroken phase, where C is topologically non-trivial, meaning it wraps a cycle or something, then in the unbroken phase, this is 0, okay? And it has to be, because there is no minimal surface that fills it in, okay? Yeah? Oh, I've not worried about factors, but I think this is a good definition for the string tension. Yeah, it's the same, right? If you take your curve to be take your curve to be two infinitely long lines. Indeed, the area is the time times the length. Yeah. No, I think it's okay. When you use the length, then you're imagining the energy is the tension times the length, right? Or something like that, right? So there's two things here. There's time and there's length. And really the two parallel things gives you a tension times a time times the length, and you tend to delete, you drop out this thing because it's not doing anything for you. Yeah, yeah, exactly. The dimensions are correct. That has dimensions of tension. Yeah, is the way to put this. Good point. Yeah. But to stress, by the way, everything I'm saying should resonate with things that, there's many ways to say these things. This is, I think, the sort of most modern way to think about it. But of course, these ideas are really well known in non-abelian gauge theory and so on. And I'll explain how this connects to things that you've heard about as we go. Good. Other questions? Yeah. Yeah.
You say you cannot directly apply that to non-abelian theory.
Yeah.
Probably something like for non-abelian theory, like the center.
Yeah, absolutely. I will discuss this in great detail in the next lecture, but indeed, in non-abelian, so what you can't do is get a non-abelian higher form symmetry, but non-abelian gauge theories have a higher form symmetry. If they're pure gauge theory, they have a one-form symmetry, which is what used to be, it's the center symmetry, yeah. It's just that's right, exactly. Yeah, exactly. It's not, the center symmetry is, however, not non-abelian, is really the point that I'm making here. Yeah. Good. Good. Other questions? Okay. So, and particularly, let me just emphasize, you might be familiar with this area law. This is, of course, a diagnostic for confinement, right? This is what we were just discussing, for confinement in non-abelian gauge theory. And I'll discuss the relationship between confinement and these things in the next lecture, I think. Okay. Good. So this is the unbroken phase, all right? And now let's go to the spontaneously broken phase. Okay, so how do we get there? So to get to the spontaneously broken phase, what you should imagine is that the things that you're counting are condensing, okay? That's what happens with normal symmetries. This operator O sort of condenses, the particles condense, okay? So what we're getting at is that the strings condense. Okay. That's a confusing statement. This might stress you out a little bit. What do I mean by strings condense? So one way to think about this is take this tension that you have here and imagine what happens if the tension drops to 0. Okay? If tension drops to 0, this area term should go away, right? And that is indeed what happens. In a phase where the symmetry is spontaneously broken, what happens is that this expectation value goes from being an area law to being a perimeter law, okay? So the area law becomes a perimeter law. okay? Where this L here is the length of the curve C. All right. So again, you can imagine inserting your curve here. And now you insert this, but it doesn't make a heavy excited state. Instead, the vacuum sort of already, these are just, by the way, just words that I'm saying now. I think they're useful words. The vacuum is instead already some sort of mess of strings, okay? So when you create this thing, it does not make a heavy excited state, okay? It just kind of sits there, all right? And then it creates, this thing will generically have the behavior of a perimeter law, okay? It's a perimeter law because, you see, there's a sort of ambiguity present in the definition of this object, all right? When I say perimeter law, what I really mean is any local functional of the curve, okay? You know, the perimeter is a local function of the curve, right? You can just create it by integrating a local density over the curve. And in reality, that kind of thing can always happen in any theory, okay? You can always have some sort of local short distance singularity present on the curve. And so you'll always get something like this, and this length is really a proxy for that, all right? So again, the thing to keep in mind is what we had in the zero form case. So again, in the zero form case, what happened was that if we had spontaneous symmetry breaking, then this thing eventually became independent and non-zero, right? It just became OO, which does not care about the separation. You could separate these things arbitrarily and it stopped caring. That is what this perimeter law is. You can make the curve whatever you like, and it doesn't really care anymore. It only cares about local data on the curve, nothing happening in the middle. All right? This is as factorized as you can get if you have a line operator. Okay? So, by the way, that actually means this parameter M is sort of very UV divergent and not really very physical. Okay? It's coming from short distance stuff. It's what we call non-universal. There is not really much information in this perimeter law thing. Okay? That's different from that. That has a lot of information, the string tension. Okay. So at the moment, this is just a name that I have given to this behavior. It's a name that is sort of motivated by what's happening for normal symmetries. It's a particular phase, which I'm calling the spontaneously broken phase. It should seem plausible, you know. But I've not told you this is useful yet. So in the lectures to come, I'll do some useful things with this, okay? I'll prove a Goldstone's theorem and stuff like that. Okay, so these are the two phases. And now, the next thing that you can imagine, of course, is what happens between the two, right? So you can imagine, for example, a phase transition. Just like in the zero form case, you could imagine a phase transition separating the two phases, all right? So, you know, what happens then at the phase transition point? Well, if the phase transition was continuous, you might expect something like this. So if continuous, you might think something like this is going to happen, okay? So this is a perimeter law, which is actually always present, all right? This M would probably be different from that M, but this is some perimeter law which is always present. This is in a sense non-universal and not interesting, but there might be some interesting behavior here. Okay? In the zero form case, we had like a power law decay, and the critical exponents for that decay were very interesting, and people have spent lives studying them. This is sort of like the analog of that for a line operator. It's like some conformally invariant function of the line of the curve C. Okay? So this would be really cool if this happens. The sad fact is that they're mostly not continuous. It turns out most transitions of this form tend to be first order. It's an interesting question as to why. I've thought about this a bit, so I'm happy to talk about it if people are interested. But they're mostly not continuous. There's one continuous example that I know of, which we'll talk about. It's a thing in 3D, the 3D Z2 gauge theory. And then people have studied this, and it's some information there. Okay? But I should say that for the most part, the phase transition turns out to be first order, and therefore not really accessible to any sort of fancy study. Yeah? Yeah. Yeah, it's true. I've not expressed that, but yeah. Indeed. So these two things are, however, different infrared behaviors for A observable, right? Once you have different infrared behaviors for A observable, I believe that implies you have a thermodynamic singularity of some sort between the two. I think one can argue that through. Okay, we can talk about it, but yeah, I think one can argue that through some grounds. So, but even if not, in all the examples that I'm going to give, they're definitely different phases. Yeah, they're definitely different phases. I think it's, okay, yeah, we can discuss that. I think I have this intuition that whenever infrared observable has a very different behavior, then there's a thermodynamic phase transition between the two. At least all examples. I agree making that into a theorem seems tricky, but we can try, yeah. But the truth is, it turns out to be just very bad. Like, it turns out these things are separated, they're not separated gently, they're separated by some terrible discontinuity in the examples that I know, which is frustrating, because I would love to apply this fancy technology to understand this thing. Okay, excellent questions. Any other questions? Good. So, so the analogy that I've stressed with the zero-form symmetry should be clear, and also it should also maybe be clear to everyone, again, exercise. Generalize this to all higher p, okay? You can sort of see how this works, right? When the symmetry is unbroken, then the thing depends geometrically on something that fills in the inside. It's like the volume of the thing filling in the inside, all right? When it's spontaneously broken, it depends only on the outside of the operator that you're looking at, okay? That's the two different classes, all right? And so I'm not going to write down any formulas, but you can imagine by generalizing the idea of area and length appropriately how that works, okay? Okay, so we're going to see this is useful. Okay, so far I've just given you some definitions. I'm going to prove to you that this is useful in the next few lectures. All right. Okay. So by the way, now is a good time, I think, to discuss some more terminology. All right. So by now we have discussed a number of extended objects. Ah, yeah, thank you. Sorry, I'll get it. Okay. Yeah. Somehow, yeah. Okay. So at this point, we've discussed a number of extended objects. So I now want to create a distinction, okay? And this is a distinction between genuine and non-genuine operators. Okay. So what does this mean? What's a genuine operator? What's a non-genuine operator? Okay. So this is just terminology, but it's a thing that I'm going to use now, so I should introduce it. So first of all, here are some different kinds of operators, okay? So number one, a topological operator is invariant under deformations of its support. Okay. So examples are this Q sub MD, which doesn't really, you can deform MD, it doesn't change. You can also imagine having a local topological operator, which is some operator which does not change as you change where you evaluate it. Okay. That's actually a very boring operator, because if it doesn't change where you evaluate it, you can prove that it's actually a multiple of the identity. Okay, so this is boring, but you can imagine you can have topological local operators or topological extended operators. These are much more interesting. Okay. Okay. Now, a genuine operator has no tail tied to it. Okay. This is a weird definition. It just means a genuine operator, most operators that you know and love in your life that you've worked with are like this, okay? So just take what field theories do I have? I have no Lagrangians on the board, but like for example, I wrote the real scalar field theory at some point today. So for example, phi of x, phi is a fine operator. You can insert it here, okay? It's good, it's a local operator. It has no tail tied to it. There is no tail there, okay? Similarly, each of these objects that we've talked about, these Q of MDs and so on, these are all genuine operators because I specify my MD, I have something defined on my MD, and there is no tail going off from this thing. It only cares about MD, okay? So here, examples are most things that you know and love, okay? Yeah?
Can you make an example where there are tails?
Yeah, that's good. That's what we're getting at next? Okay. So, following that suggestion, number 3, a non-genuine operator. Which again can either be local or extended, has a tail. Okay? And now I'm going to, again, erase the board. And everyone in the meantime, think about your favorite operator with a tail, and then I'm going to do some examples momentarily. Oops. Oh, I even had a board. Okay. Still learning the arts of German board usage. Okay, good. So, so now let's. Okay, people have thought of examples of operators with tails. Anyone have one they want to share? No one? Okay. So here are some examples, okay? So number 1 is fields that are charged under gauge symmetries. Okay. So for example, let's imagine a QED with a charged scalar attached to it. Okay, so I have my my QED, and then let me couple in a charged scalar field. Okay. Now my phi of x, this thing transforms under the gauge symmetry, right? So it's not something, you can't really write this down, okay? This is a gauge variant object. Because it transforms under the gauge symmetry, it does not actually exist, all right? So what do? You tie a Wilson line to it, right? So you do something like this. You have an integral of your Wilson line on some curve that starts here. This notation is not very precise. It's on some curve, but the endpoint of the curve starts at this point x, and then it goes off to somewhere where you worry about it later, okay? This operator phi has a tail tied to it, okay? It is not genuine. All right? Okay. Now, notice that here you are unlikely to forget about the tail, right? In particular, this Wilson line that goes off from here, it depends on the curve C. It does stuff, all right? And you're therefore unlikely to forget about the curve. And this is an example where the tail is not topological. All right? Something else that can happen is you can have cases where the tails are topological. All right? This is a bit more insidious because because the tail is topological, you might not notice it and then get into endless confusion about whether or not it's there. Okay? It's not going to happen here. No one's going to forget about this Wilson line. But there are cases where you can forget about the tail. So I want to now work out an example where the tail is topological, just to show you that these things can happen. Okay? It's going to be a very simple example. And finally, I should mention that this sort of thing can happen both for local and extended objects. So for example, you could have a line operator, okay, that has a tail, where the tail in this case is a surface, okay? So there's some surface S coming out from it, where the boundary of that surface is C, and where S is topological. Or rather, the operator defined on S, that's the analog of this tail, is topological. This can happen, all right? This is the higher dimensional analog of that. All right? So it is important to distinguish these things from each other, all right? And I'm now going to work out an example quickly of a non-genuine local operator, all right? Any questions about the lingo before I give this example? Everyone happy with the lingo? Okay. So here's an example of a non-genuine local operator. Okay, with a topological tail. So it's not a simple one like that, all right? So this section requires you to know a little bit about 2D CFT, so I apologize for that. But I think you can follow the ideas even if not. So I want everyone to consider the following 2D CFT. The 2D CFT that I think everyone knows and loves, the free compact boson. Okay, free 2D compact boson. Okay. So theta is the field that I'm interested in, and theta is periodic with periodicity 2 pi. All right. There's some information in this G. Because theta is periodic, this G has information in it. This is what you might call people call this the radius of the boson. I'm keeping the periodicity fixed, but that's the idea. There's a single marginal parameter, which is this G. Okay. Let's study this on S1 cross R. Okay. So in other words, here's my cylinder. Okay. This one is time, and I'm going to call this direction phi. Phi is the direction around the cylinder. Okay. And phi is also periodic with periodicity 2 pi. Okay. Okay. Now, people know about the state operator correspondence, seeing some nodding, but not universal nodding. The state operator correspondence in 2D conformal field theory relates states on the cylinder to operators on the plane. Okay? So basically, if you have any state here, you do what's called the exponential map, and you get an operator on the plane from there. Okay? So for example, if you take the vacuum on the cylinder and the state operator correspondence, then you get the identity operator on the plane, which is, doesn't do anything. It's the most boring of operators. So now we're going to run the state operator correspondence in a slightly more interesting way. Okay? So let us consider the vacuum on the cylinder on S1 cross R with twisted boundary conditions. Okay? So for example, let's consider the following boundary condition. That when I go around the spatial cylinder, I also go around the target space circle. Okay? So this is a twisted boundary condition. Here, n is an integer. I can pick it to be anything I like. And I'm saying that when I go once around the spatial cylinder, I also go once around the target space direction. Okay? This is a completely reasonable thing to do. Okay? Okay. So the vacuum with these boundary conditions defines a state which I'm going to call n. Okay? And now, given this vacuum state, I can do the state operator correspondence to get some operator on the plane. Okay? So I take my vacuum with my twisted boundary condition, I map it back to the plane, I get some operator. I'm going to call that operator v sub n of x. Okay? This is a completely fine operator. Okay? It has no tail. It's just an operator. Perfectly fine operator. Okay? Notice that I could have formulated it directly on the plane. To formulate directly on the plane, the way in which I would do it is, I would take a point x and I would demand that the integral of my curve, of my target space field S theta on some small curve surrounding that point is a multiple of 2 pi. Okay? This is another way to define this operator. I say in my path integral, always demand that the field theta wind around by some integer number of times. Okay? That defines some sort of local disturbance on the plane. That local disturbance is what we would call Vn of x. This is another example of this thing that we talked about during the tutorial yesterday. This is called a disorder operator, because it's defined in terms of a boundary condition on the path integral. Okay? So there are two different ways to define this. They're really the same thing. Okay, everyone happy with this? This is a genuine disorder operator. Maybe I should write that down. It's also genuine. Okay. Now let's do something which feels wrong. Let's now go back to the cylinder and study a different boundary condition. Let's study the boundary condition where theta of phi plus 2 pi is equal to theta of phi plus 2 pi alpha, where alpha is not an integer. Okay? In other words, I am demanding that when I go around the cylinder, I do not come back to an integer number of windings around the thing. This feels wrong in some way, right? And what I'm trying to push on is, why does this feel so wrong? Okay? You see, physics on the cylinder, it'll be okay. I mean, the boundary condition is a bit weird, but okay, you can still calculate things, short distance singularities, everything will be more or less all right. Is there something still off about this object, right? So in particular, the vacuum with this terrible boundary condition is a state which I'm going to call alpha, all right? And now you can again do the state operator correspondence, okay? And again get some operator on the plane, but now this operator has an issue, right? You see, the point is, what this operator does is, it demands that if you go around it, theta does not come back to a multiple of 2 pi, it comes back off by alpha, right? In other words, if theta is 0 here, when you go all the way around from this, it comes back to be off by 2 pi alpha, where alpha is not an integer. This is not the same as that, okay? So there's something happening on some cut that emanates from this object, all right? This is an example of a non-genuine operator, because this cut carries some sort of information, all right? However, it's also clear that this cut is topological. It does not affect any local physics, yet nevertheless something still happens when you go through it. Okay? This is a simple example of how you can get into problems if you don't worry about these things. And also, I just want to stress that you can think about this object. It's okay. You just have to remember it's tied to a line. Okay? That's all. All right. Any questions about this? Yeah.
How do you know it's a feature, not a bug?
Well, those are, I feel, subjective words. You know, one man's feature is another man's bug. It's just a fact that this is what happens, I think. Maybe when you explain, yeah. Yeah.
For someone not experienced in this,
Yeah.
it looks like just an ill-defined operator. How do you...
Oh, I don't think it's ill-defined. I mean, you can insert this in correlation functions and calculate things with it. Yeah. Yeah.
At least for those boundary conditions, they
Yeah.
really look like ill-defined boundary. On a cylinder, not on a plane.
Oh, on the cylinder, I think it's fine. We can do some calculations and see. I think it's all right. It's not the end of the world. I mean, you know. In string theory, sometimes we put two D-branes, right, that are separated from each other. It's basically this boundary. You know, it's not crazy. You know. Yeah.
Somehow identify this point.
Yeah. Yeah.
Some point and find 0.5 plus 2 pi.
Yeah.
But this
Yeah, I mean, theta is, so this is interesting. Theta is, indeed, so the branch cut is there. This is really, this cut also exists in the cylinder. So the branch cut is there. Theta is sort of only locally defined in that way. So what that means is that whenever you work with this, you have to remember that there's a cut coming off of it. However, if you work with the cut, then it's actually completely fine. I think that's what we're trying to say. It is so this is the sort of thing I think I want to push on. It is an ill-defined local operator, but with the cut, it's fine, in that there are unambiguous answers for everything you want to calculate. This is what I want to stress. Normally, you would really think about this as the endpoint of a topological operator. That is, I think, a way of phrasing it which makes it seem less emotionally charged. And in the exercise session today, we will understand what this topological operator is, of whom this is an endpoint. I think that's another way to think about it. Yeah. This kind of thing, by the way, I realize I don't think Nele has done this yet, but you're going to revisit this in the entanglement entropy lectures, where there are, again, cuts and operators on the endpoints, and the operators on the endpoints carry a lot of information. This is a similar thing. Yeah.
This picture drawn here with the cut is in the time space, right? It's in the space.
Oh, no, sorry. This is on the plane, excuse me. So this is on the plane. So my local operator is here, okay? And this cut is just saying that a line comes off of it. The location of the cut is irrelevant, yeah. The target space is just a circle, yeah. So if the theta was 0 here, it's 2 pi alpha here, okay? Yeah. Okay, good. So in the exercise session today, we'll think more about this, and in particular, this topological line, it has an identity that you actually already know, sort of, and we'll discuss that a bit more in the exercise session. Okay, so this is an example, and with this in mind, let's now actually move on to some applications of the higher form symmetry stuff. We'll see higher form versions of this, which is really why I want to introduce this. Okay? Okay, so here we go. So now, this is chapter 3 of my notes. Finally, we get to the fun stuff, which is applications. Okay, thank you. All right. So the first application, application number 1, is free electromagnetism. The very first field theory that most of us encounter in our lives. Who would have known that free electromagnetism with no matter, so the action is S of A equals to integral d4x 1 over 4 e square f square. This guy, where F is the field strength tensor for my gauge field A, okay? This is the thing we're going to study first. As I mentioned earlier, this has 2 one-form symmetries, okay? So first, an important point. When someone gives you something like this, okay, a gauge theory, they actually have not yet fully specified the theory, okay? They specified the action, and the action depends only on the Lie algebra of the gauge group, but they also need to tell you a bit about the sort of global properties of the gauge group, okay? So in particular, I'm telling you now that the gauge group is U1. So this is compact U1 gauge theory. Okay? What that means is that gauge transformations are labeled by G, which is an element of U1. Okay? And under a gauge transformation, A goes to G inverse A plus DG. This is, of course, a bit unnecessary for Abelian, but you get the idea. I'm just writing it this way to emphasize that G is an element of U1. Okay? Okay. Now, what are the symmetries of U1 electromagnetism? So again, textbooks now talk about gauge symmetry and blah, blah, blah. But by now, we're a very sophisticated audience. We know that gauge symmetry is a lie, and it's a redundancy of the description, blah, blah, blah. And it's not a symmetry at all. So what we should now ask is, forget about gauge symmetry. What is the sort of invariant physical information in this theory? Okay, this is a bit pretentious. I'm talking about E&M, but still, we can ask, what is the invariant physical information? In other words, what are the global symmetries in this theory? Okay? And this theory has 2 one-form symmetries. Okay? So there are 2 one-form symmetries, one-form global symmetries. And they are U1, okay, let me write this slightly differently. So from now on, I'm going to use a notation where I write the symmetry group. At the top, I write the forminess of the symmetry. It's a one-form symmetry. So pick it as an electric U1 one-form symmetry. And its current, J mu nu electric, is equal to 1 over E squared F mu nu. And is also a magnetic one-form symmetry. And its current, J mu nu magnetic, is equal to 1/2 epsilon mu nu rho sigma F rho sigma. Okay? These are the symmetry currents for the electric and magnetic one-form symmetries. Okay? And let me also write this in form language. In form language, JE equals to 1 over E squared. Oh, sorry. There's a 4 pi here, which is important. Okay. So JE is 1 over E squared times F. And Jm in form language is equal to 1 over 2 pi star F. Okay. So these are both conserved, right? All right. So d mu j mu nu electric equals to 0. And that follows from the equations of motion of this theory, which I did not write down. The equations of motion of free E and M, of course, are that d mu f mu nu equals to 0. From varying this action, you get this. And that, of course, means that d mu j mu electric is 0. Okay? Physically, what does this mean? Physically, this current counts electric field lines. This is saying that electric field lines do not end. Okay? They don't end because there's no matter in the theory, right? There are no electric charges here. So that means electric field lines can't end. Okay? In other words, no electric charges. All right? Okay. That's fine. And now how about the magnetic one? It's also true that d mu j mu nu magnetic equals to 0. So this does not require the equations of motion, right? This just follows from the Bianchi identity. So this is from Bianchi. And again, physically, it's saying that magnetic field lines don't end. Because there are no magnetic monopoles in this theory. No magnetic charges. Okay. So from now on, what we're going to do is we are going to study the phases of electrodynamics. There are actually a few phases of electrodynamics. We're going to study them from the point of view of these symmetries. Okay. Are there any questions about these symmetries before we keep going? Yeah.
So now you mentioned what are the conservation laws, but you didn't really say what are the symmetries. So what is, can you tell about that?
So the point of view that I want to take is that if you have these topological defects, that is the symmetry. Okay? So I think what you're asking is, how does the symmetry act on the fundamental fields? Is that right? That's what I think you're asking. Yeah.
I can't understand the symmetry of nature.
Correct, yeah. So what I'm really advocating, to be honest, here, so first of all, I will answer that half in a second. But I think what I'm really advocating is that the thing that we call a symmetry, you can define from the existence of these topological operators and not from how that actually acts on the fundamental fields. The reason I'm pushing for this weird thing is that there are often many symmetries that don't act in a simple way on the fundamental fields. Okay. Having said that, the electric symmetry acts in a simple way on the fundamental fields, which I'll say in a second. The magnetic one does not actually act on the fundamental fields in any useful way at all. And so that's why I'm advocating this. Yeah. So for any symmetry, I think it's not so obvious what that means. But yeah, let me get to this in 1 second. Yeah. You can actually, people can probably already guess how the electric symmetry acts on the fundamental fields. But I'll get there in a second. Yeah. No. Oh, did it fall off? No, I think maybe we can keep going and you can tell me where. Because I mean, again, the gauge symmetry is just a symmetry, just a redundancy, blah blah blah. It's important that everything be invariant under that redundancy because that redundancy is built in. But I'm not making any assumptions about anything. Yeah, I think I understand what you're channeling. You're channeling this idea of an asymptotic symmetry where you have an infinite boundary and you demand that certain parts of the gauge transformations are not gauge anymore in some sense. And I'm not actually making any assumptions like that. Like this electric flux is conserved at all points in the interior of the space, not just at infinity. Okay. Of course, you can also measure it at infinity because you can deform the operator away to infinity, but it's locally conserved. Okay. So I'm not assuming this. This symmetry exists even in the presence of an arbitrary gauge parameter. Okay. Yeah. Yeah.
How do I see that these equations correspond to these field lines not ending? Because, for instance,
Yeah.
the way that I think about electric and magnetic field lines
Yeah.
is like, in undergrad when you're drawing out
Yeah.
how the electric field looks, you
Yeah.
Now we seem to be talking that these lines kind of just represent how strong
Yeah.
the magnetic or
Yeah,
electric
yeah,
field is in a particular region.
Yeah.
Whereas now we seem to be thinking about them as real objects. So
Yeah. So this is part of this is just motivational, to be honest. So one way to think about it is actually just break this down in a rest frame, right? Pick a rest frame, and then look at the components of that, and you'll see one of the components, in particular, usually the time component of this symmetry equation. So set nu equal to t. That will always take the form of divergence of some spatial vector. Once you do this terrible thing of sitting in a rest frame, then the t component of this will always look like divergence of some 3-vector field equals to 0. And therefore, you can identify what the 3-vector field is. In this case, it's the magnetic field. In the other one, it'll be the electric field. So that's one way to identify it. Now, there's something a little deeper here, though, which is that to what extent are magnetic and electric field lines real objects? And one can think about this. You see, it's clear that for any configuration of electromagnetic fields, you can always draw these lines, right, these arrows. That's often a useful thing to do. Whenever I think of E&M, I do imagine that. But there's also a sense where they're not real objects because they're very fluffy, right? They really spread out. You cannot obviously pin down one electric field line and say, look, here is my field line. It sits there. And that's actually, there's a deep reason for that. It's because the symmetry, okay, I don't want to give away the punchline. Let me keep going, and then at some point I'll say, this is the punchline. It's anticipated by that. Yeah, okay. So spoilers. But we'll come back to that in a second, okay? There are cases where you can pin down one electric field line, but it's not in this theory, all right? Okay, I realize that I'm running a bit short on time, so let me just say one more thing, and then we'll stop. So this relates to your question. So you should ask, what are the charged line operators? Okay. So, what are the line operators who are charged under these symmetries? So first, under U11 electric, the charged line operator is the Wilson line, okay, which is defined in terms of oh, wow, I've messed up the writing of this. It's defined in terms of the gauge field in the way that everyone knows already. Exponential IQ integral of A. Okay? This is the U1 Wilson line. Okay. In particular, in the presence of the Wilson line, we should compute the divergence of that object, and make sure that this satisfies the ward identity that I put somewhere over there, all right? And it does, right? The way to see that quickly is insert this into your action. That basically adds a term e to the IQA into my action, and then vary the action to find the equations of motion. There will be a delta function contribution on the right-hand side of this guy, okay? And it will create the right ward identity that I want. If you go through this exercise, which maybe I should make an official exercise, you find that in the presence of the Wilson line, d star j electric, okay, times wq of c is indeed equal to iq, this Fermi delta function, times wq of c. Okay, so this is an exercise that you can do. In other words, this is the right ward identity. Okay. And I should stress, because I'm doing compact E and M, these charges Q are integers. All right. I have actually not told you about my normalization of things properly here. I should have done that. But I am normalizing things so that these charges Q are integers. Okay? Now, I want to point out that in this case, the action of the one-form symmetry on the dynamical degrees of freedom can actually be easily understood. Okay? So what is the action of U1, 1e on the dynamical degrees of freedom, in other words, on A? Well, the action is simple, right? You take A and you shift A by a one form. This lambda is a one form where this one form is closed. Okay? D of the one form is 0. Okay? This operation clearly leaves invariant that action, because the action only cares about D of A. This is a closed one form, and this is another way to understand why this is called a one-form symmetry. Okay? The invariance of the action, the invariance of the action of the symmetry is parametrized by a closed one form. Note that under this object clearly transforms by a phase, right? So I will just put this here because it's the last formula I'm writing down today. Under this object, under this transformation, wq of c transforms as e to the iq integral of c lambda times wq of c, where this is this one form. All right? And this is another way to see that w is the charged object under this symmetry. All right? Now, this is something that we can do in this case, but as I was mentioning to you earlier, so in this case, just to stress, I can show you how it acts on the fundamental degree of freedom. But we're going to see that in a lot of cases, it's just not going to be so obvious. All right? In particular, the magnetic case we're going to do in a second, there is no simple way to write this thing down. And that doesn't mean that the symmetry has no behavior. I think that a lot of the insights that have come from this have been from realizing that even when you can't figure out exactly how the symmetry acts on the fundamental fields, nevertheless, the symmetry has dynamical consequences. I think part of the power of this field has been from realizing that and really pushing on that. Okay? So that's what we're going to keep exploring in the next parts. Okay, that is all for now. Your homework for the next hour is figure out what the charged object is for the magnetic thing. Okay, and yeah. Okay, you know how to do this. We did it already yesterday, but think about it. Okay, that's all. I'm done.